Your Perception Deceives You, Beyond the Physics. Written by Theo E. David and presented by the Audiobook Shelf. Introduction. To better understand how quantum physics has reshaped our understanding of the universe, it is essential to examine how it questions some of the long-held principles of classical physics. Classical physics, rooted in the works of Newton and Maxwell, posits a deterministic and predictable universe. In this view, if you know the initial conditions of a system with enough precision, you can predict its future behavior with certainty. Newton's laws of motion and Maxwell's equations governing electromagnetism epitomize this predictability and determinism. However, quantum physics, developed in the early 20th century by pioneers like Max Planck, Niels Bohr, and Albert Einstein, introduced concepts that fundamentally challenge this deterministic view. For example, wave-particle duality represents one of the most significant divergences from traditional physics. In classical physics, particles and waves are distinct entities. However, depending on the observational setting, particles like electrons exhibit both particle-like and wave-like features, as demonstrated by quantum experiments like the double-slit experiment. This duality implies that reality's nature is more complex than previously believed and goes against classical intuition. Heisenberg proposed the Uncertainty Principle, which states that certain combinations of physical attributes, like momentum and location, cannot be measured simultaneously with arbitrarily high precision. In classical physics, such qualities can be measured precisely and simultaneously, but there is no such restriction in quantum mechanics. Quantum entanglement describes how particles, regardless of distance, get entangled to the point that their states instantly affect one another, challenging the classical notion of location and non-local interaction. The superposition principle further illustrates the differences between classical and quantum physics. According to classical physics, a system is always in one state. Quantum mechanics, on the other hand, permits superposition, the simultaneous existence of several states of a quantum system up to measurement. These illustrations highlight how the deterministic, local and singular state assumptions of classical physics are challenged and expanded upon by quantum physics. Empirical evidence from multiple experiments confirms these quantum ideas and emphasizes the need for a new framework to comprehend the fundamental laws of the cosmos. These basic changes have allowed quantum physics to drastically alter our understanding of reality and provide a richer, more fascinating picture of the universe. Certain phenomena are philosophical and religious, because they defy the laws of classical science. Classical physics, based on the ideas developed by Newton and Maxwell, provides a deterministic and predictable picture of the cosmos. However, some experiences and occurrences appear to go beyond this viewpoint, including perceptions of the transcendental or divine consciousness, experiences, and the nature of the soul. Faith and philosophy are turned to for answers, as traditional science is unable to sufficiently handle these elements. This is where quantum physics shows itself, departing from the logic laid down by classical physics. A comparison between classical paradigms and quantum physics is essential to comprehending the tremendous implications of quantum mechanics. Beyond expanding the limits of human awareness, quantum physics challenges the basic beliefs about reality ingrained in classical frameworks. By contrasting these two viewpoints, we can recognize how quantum theory is revolutionary and goes beyond the traditional bounds of our knowledge. Energy becomes a primary area of research in quantum physics, as it is the fundamental substance from which all phenomena originate and develop, serving as the cornerstone upon which the universe is constructed. Energy is a complex dance that underlies all motion, transformation, and condition that matter can acquire. This idea is firmly rooted in the principles of physics and is not just an abstract philosophical concept. Energy's omnipresence and influence are indisputable, and it is quantifiably and qualitatively described in numerous laws of physics. According to the fundamental tenet of classical physics, the principle of energy conservation, a closed system's total energy stays constant over time. This law governs our comprehension of the dynamics of the cosmos and directs our investigation of important questions regarding its nature. One of the main questions raised by the conservation of energy is whether the universe's total energy content is unchangeable. This deep-cut question asks us to consider whether energy is limitless or finite, and, if finite, what consequences such bounds would have for the ultimate destiny of the universe. Moreover, the conservation of energy poses fascinating queries concerning the source of the universe's energy. Did it originate from nothing, exist in some form forever, or was it introduced into the universe at some point in the past? This investigation of the origins and evolution of the universe explores the fields of theoretical physics and cosmology. Numerous observations and experiments provide scientific evidence in favor of the energy conservation principle. The principle of energy conservation governs all aspects of the behavior of the universe, including the motion of celestial bodies and the interactions of subatomic particles. In addition, theories like the laws of thermodynamics offer more information about how energy has shaped the past, present, and future of the universe. A deeper exploration awaits you when you enter the fascinating world of quantum physics and the boundaries of human perception. As the curtain rises, we will explore the tremendous consequences of quantum theory and its intricate tapestry. In this engrossing voyage, we will explore the cosmos together and consider the mysteries that influence our perception of the universe and our specific role in it. Redefining the limits of human perception, the law of energy conservation effectively illustrates the idea of cause and effect. It is evident that a cause, the original form of energy, produces in effect the end form of energy, as one form of energy transforms into another while preserving a direct proportionality. In his groundbreaking study, Julius Robert Mayer stated, "It is as difficult to explain the production of heat as it is to give any account of the motion that disappears without the recognition of a causal connection between motion and heat." As Mayer pointed out, the indestructibility of causes means that energy alters its form rather than its quantity, preserving an endless cycle of cause and effect. James Jouley's rigorous studies on energy conservation helped to further quantify this idea. He proved that heat is always produced when there appears to be kinetic energy destruction or absorption, frequently as a result of friction. According to Joule's experiment, heat is produced any time a life force appears to be destroyed or absorbed. Enshrined in the scientific method, as well as theological contemplation, his conclusion stated that everything may appear complicated and involved in the apparent confusion and intricacy of an almost endless variety of causes, effects, conversions, and arrangements. Yet the most perfect regularity is preserved, the whole being governed by the sovereign will of God. Jouley's recognition of divine influence underscores a critical intersection between physics and theology. The precision of mathematical descriptions of energy transformations suggests to many early scientists a purposeful divine action. This perspective aligns with theological premises that every contingent being, defined by its changeability, must have a beginning and therefore a creator. The conservation law's assertion that energy can neither be annihilated nor created out of nothing hints at an eternal source, a creator beyond human capability, reinforcing the idea that energy itself is a divine creation. Biblical references, such as Genesis 1:1-3, "And God said, 'Let there be light,' and there was light. And God saw that the light was good, and God separated the light from the darkness," highlight transitions beyond human capacity, suggesting divine intervention. This transition from darkness to light symbolizes a transformation that underscores divine power, further emphasizing that such fundamental changes in energy and existence are the domain of the divine. Thus, the law of energy conservation not only anchors our understanding of physical phenomena, but also invites a deeper contemplation of the universe's metaphysical origins, blending scientific inquiry with theological insight. Is the universe aging? The law of conservation of energy asserts that the total amount of energy in the universe remains constant, neither created nor destroyed. However, the second law of thermodynamics delves deeper, addressing the natural tendency of energy to disperse and become less organized over time. This law not only explains the distribution of energy, but also introduces the concept of the arrow of time through irreversible processes. Consider everyday examples. A shattered vase cannot reassemble itself, colors in clothes and paint inevitably fade, and dust accumulates in an empty room. These irreversible changes illustrate how systems move toward states of equilibrium unless acted upon by an external force. Such processes underscore the non-cyclic nature of physical phenomena, reinforcing the idea that time progresses in a single direction. William Thomson, in his study of heat and energy dissipation, articulated that heat flows from hot to cold regions, and once thermal equilibrium is reached, no more work can be extracted from the system. This principle of heat transfer highlights one of the most common irreversible processes and reflects the inefficiency inherent in energy utilization. Our everyday experiences reveal that no engine can ever achieve perfect efficiency. The dissipation of heat, often seen as lost energy, is central to understanding the second law of thermodynamics. This continual loss of usable energy raises the specter of the universe's ultimate fate. If energy distribution continues unchecked, the universe may reach a state of thermal equilibrium, a heat death, where all biological processes cease due to the lack of available energy. This notion aligns with the second law's implications, but also prompts us to question its assumptions. The second law typically applies to isolated systems with a fixed energy amount. However, this assumption may be flawed given our limited knowledge of the cosmos. The universe might receive bursts of energy from unknown sources or contain latent energy beyond our comprehension. Thus, the closed world assumption lacks sufficient evidence, suggesting we should remain open to alternative interpretations. Moreover, while the second law predicts a trend toward disorder and inefficiency, nature provides numerous examples of growth and regeneration that seem to defy this principle. New life continuously emerges, organisms grow stronger, and processes like photosynthesis convert waste into vital resources. These phenomena indicate that not all processes lead to decay and extinction, some drive toward renewal and vitality. While the second law of thermodynamics explains many patterns of energy flow and inefficiency, it does not account for all aspects of natural processes. The interplay between energy dissipation and the emergence of new life suggests a more complex reality where growth and decay coexist, challenging the notion of an inevitable march towards chaos. Entropy, chaos, or control. Entropy, the quantitative measure of heat transfer from warmer areas to cooler ones, is a fundamental concept in thermodynamics. Mathematically, entropy is formulated to always increase when heat is redistributed within isolated systems. As these systems evolve, they transition from less probable configurations to more probable disordered states. Thus, entropy can be seen as a gauge of disorder. To illustrate, consider a deck of cards perfectly sorted by suit and rank. If we shuffle the deck, the neat arrangement quickly becomes a random jumble. The same is true of a garden. If not tended regularly, weeds will invade the carefully planted flowers. These examples demonstrate that maintaining order requires continuous effort and deliberate intervention. The essential point is that in isolated systems, entropy, or disorder, invariably increases. However, the universe displays an extraordinary level of order. Planets do not collide with each other, and Earth orbits the Sun with precise regularity. This high degree of order suggests that the universe is not an isolated system. On the contrary, it appears to be continuously maintained by a transcendent creator whose nature is fundamentally different from that of the universe. The hidden forces. The journey to understand force and fields in physics is a tale of evolving perspectives and groundbreaking discoveries. Newton's laws of motion offered a straightforward view: force as a tangible interaction between objects, an idea that was as intuitive as it was widely accepted. However, the advent of electricity and magnetism electrified the scientific world, compelling thinkers to reconsider this simplistic notion. William Gilbert's exploration of magnetism and Ørsted's revelation of the connection between electricity and magnetism were pivotal. These discoveries hinted at deeper, unseen forces at play. It was Michael Faraday's ingenious experiments that truly upended conventional wisdom. A fluctuating magnetic field could generate an electric current, a phenomenon that suggested action at a distance. This provocative idea ignited a fierce debate about the nature of fields. Were these fields mere mathematical abstractions, or did they have actual tangible existence? The titans of physics like Newton, Faraday, and Maxwell staunchly argued for the latter. Faraday, in particular, was adamant that magnetic fields were real, even if invisible to our senses, and Newton dismissed the notion of forces acting across a vacuum without some mediating entity as absurd. Yet in the modern era, perspectives diverge. Richard Feynman and others view fields as pragmatic tools, useful for describing interactions but not necessarily real entities. This contemporary skepticism keeps the debate alive, questioning the reality of fields and their critical role in preserving the principle of spatial locality in physical interactions. Thus, the discussion of force and fields is not just a historical footnote but a vibrant, ongoing dialogue that challenges our understanding of the universe. It invites us to ponder: are we merely mapping interactions with abstract constructs, or are we uncovering the very fabric of reality? The answer remains as elusive and tantalizing as the fields themselves. The evolution of physics, from ancient foundations to quantum realities. There have been several epochs in the history of physics, all characterized by significant discoveries and advances in knowledge. Algebra and geometry developed throughout the First Era, characterized by the flowering of Islamic civilization. The use of these mathematical advancements in optical and astronomical applications led to the development of advanced astronomical instruments and accurate records of planetary motions. During this time, water-powered actuators and clever mechanical devices also became popular. Under Western civilization, the second period took place 3 centuries after the 17th century. Calculus was established during this period, along with the discoveries of electricity and electromagnetic theory. Physics played a passive role in these 2 periods, explaining the inanimate universe and rigorously keeping the observer and the observable apart, upholding the causality principle. This causality is demonstrated, for example, by the law of conservation of energy, which states that energy can only change forms while preserving direct proportionality between original and end quantities. But the 20th century brought about a significant change, leading physics on an amazing revolutionary journey that we now refer to as modern physics. Pioneering findings that contradicted conventional wisdom completely changed modern physics. Black-body radiation tests conducted by Max Planck in 1900 showed that the light emitted by black bodies has distinct intensities that are multiples of a constant subsequently named after him. The concept of quantized light intensity was incompatible with the constant changes predicted by classical physics. Planck first insisted that light returned to its waveform after interacting with the heated body, notwithstanding his results. Einstein audaciously expanded on Planck's quantum theory to include the nature of light itself. In 1905, he proved that light might behave like particles by releasing electrons and transferring energy to a metal plate through the photoelectric effect. Planck had not made the breakthrough step of realizing that light behaved like a particle. With his model of the hydrogen atom, which showed energy levels as discrete and divided by prohibited gaps, Niels Bohr improved quantum theory in 1913. This model related atomic structures to quantum effects seen in light. Early physicists observed phenomena like interference, diffraction, and reflection and saw light as a wave, influenced by the work of Alhazen in the 10th century. In the 19th century, Maxwell repeated these concepts mathematically. However, light's dual existence as a wave and a particle was demonstrated by Einstein's work. De Broglie proposed in 1924 that electrons might also display this duality, and Davison and Germer supported his theory in 1927. This created a framework for all particles to have both particle-like and wave-like characteristics. This idea, called wave-particle duality, has significant ramifications for contemporary physics. Complications of quantum reality. Quantum physics introduces challenges that defy common sense. 2 of the most perplexing issues are the notions of observer-created reality and inherent randomness. In daily life, objects exist independently of observation. However, quantum mechanics suggests that observation itself determines the state of quantum events. The double-slit experiment illustrates this concept. A stream of electrons passing through 2 slits forms a diffraction pattern on a screen, displaying wave-like properties. When the electron intensity is reduced, the diffraction pattern is not immediately visible, but individual electrons still land on the screen in a pattern that corresponds to the diffraction pattern over time, showing particle-like properties. Supporters of the observer-created reality argue that the act of observing electrons on a screen determines their positions. This idea, proposed by John Wheeler, suggests that while the positions on the first screen are random, they become predictable on a second screen behind it, implying that observation creates reality. Critics question this notion, arguing it defies human sense and undermines the foundation of knowledge acquisition. Fundamental questions arise. How can an observer lacking knowledge of the observable bring about its existence? What defines the properties of the observable, the observer's ignorance, or the indeterminate nature of the observable itself? Given that quantum observables constitute the universe, how does our world function if its fundamental elements lack inherent reality? The second intriguing phenomenon in quantum mechanics is the baffling behavior of electron transitions. When electrons jump to higher or lower energy levels, they absorb or emit photons, respectively. This might lead one to assume a straightforward causal relationship: shine a light beam on matter, and electrons move up an energy level. However, reality defies this simplicity. Electrons spontaneously move up and down without any change in the experimental setup, and the time they remain in an excited state is not fixed, it varies unpredictably. Physicists refer to this as inherent randomness, a term that essentially means the trigger behind these electron movements is unknown. This randomness, though puzzling, is not unique to quantum physics. It also appears in everyday scenarios. For example, when high-pressure gas is released into a container through a small hole, the gas molecules spread out randomly within the container. Here, randomness reflects our lack of interest in tracking each molecule's behavior, focusing instead on the gas's overall behavior. In principle, we could determine each molecule's path to its rest position. In quantum physics, however, we cannot discern what causes electrons to jump between energy levels or why these jumps occur at specific moments. The mystery deepens as we confront our inability to uncover the underlying phenomenon that drives these electron transitions. The Copenhagen interpretation. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, offers a practical approach to quantum phenomena. It posits that quantum physics deals with probabilities rather than certainties. Schrödinger's wave function provides a mathematical framework for predicting the probability of finding a particle in a given region. Heisenberg's uncertainty principle states that precise measurement of one property, such as position, increases the uncertainty of another, such as velocity. This principle is exemplified in the double-slit experiment, where the diffraction pattern requires a monochromatic electron beam, leading to uncertainty in electron positions. Bohr introduced the concept of complementarity, asserting that atomic particles have properties that cannot be simultaneously measured. Understanding quantum phenomena requires measuring both wave-like and particle-like properties, though these properties cannot be observed concurrently. Embarking on the journey through physics, we navigate a landscape where certainty fades into uncertainty and reality bends to the influence of observation. This odyssey challenges our understanding of existence, inviting us to reconsider the very fabric of reality itself. Dispute among scientists. The claim that microscopic objects lack reality until observed has been a source of contention among Western physicists, particularly disturbing figures like Einstein and Schrödinger. They both dismissed this interpretation outright, with Einstein famously quipping, "I like to think the moon is there, even if I am not looking at it," emphasizing his belief that particles must possess an independent reality apart from measurement. This disagreement sparked significant debate between Einstein and Niels Bohr, both in conferences and academic papers. The key to the dispute was the dual nature of light. The heart of the clash between Einstein and Bohr was the enigmatic dual nature of light behaving both as particles and as waves. This paradox was not merely a technical detail, but a profound mystery that challenged the very foundations of physics. While both Einstein and Bohr agreed on the particle-like behavior of light, their discord centered on its wave-like nature. This wave-particle duality, a cornerstone of quantum mechanics, was where their intellectual battle lines were drawn. Bohr's vision, a world of fuzziness. According to Bohr, an atom loses its identity as a concrete particle and becomes nebulous and undefined when it participates in a diffraction pattern. Bohr thought that this change was a direct result of the uncertainty principle, which states that the more accurately we attempt to measure one of a particle's properties, like position, the less precisely we can determine another characteristic, like momentum. Therefore, rather than the atom being a defined entity, Bohr believed that the act of measurement itself forced the atom into a condition of ambiguity, a cloud of probability. Einstein's counter, persistent particles. But Einstein remained unwavering in his conviction that atoms always remain particles, even when they are involved in wave-like events. The idea that reality could vanish into nothing more than chances and uncertainties was too much for him to bear. According to Einstein, the concept that an atom could become a fuzzy wave and lose its unique characteristics ran against the fundamental principles of physical reality. His famous comment, "God does not play dice with the universe," captured his disquiet over the uncertainty and unpredictability that Bohr accepted. Clash of philosophies. This dispute wasn't just about the behavior of light, it was a profound clash of philosophies. Bohr's perspective was rooted in the empirical, accepting that our observations define reality. For Bohr, the limits imposed by the uncertainty principle weren't just mathematical boundaries, but fundamental aspects of nature itself. He saw the fuzziness not as a flaw, but as a feature of the quantum world. Einstein, on the other hand, was driven by a deterministic view of the universe. He believed in an underlying order and predictability, a reality that exists independently of our observations. Einstein sought a deeper, more concrete understanding of nature, one that would ultimately reconcile the particle and wave aspects of light into a unified theory. The ongoing debate. Their debates, intense and often heated, were more than academic exercises. They were battles for the soul of physics, each representing a different vision of what science should be. Bohr's triumphs in these debates helped shape the Copenhagen interpretation, which has become the standard framework for quantum mechanics. Yet Einstein's objections laid the groundwork for future explorations into quantum theory, influencing generations of physicists. Einstein's challenges to Bohr reached their zenith at the Solvay conferences in 1927 and 1930. These gatherings became the stage for Einstein's ingenious thought experiments, meticulously crafted to expose perceived flaws in Bohr's interpretation of quantum mechanics. During these conferences, Einstein proposed scenarios that, on the surface, seemed to defy the principles Bohr held dear. His thought experiments were not just hypothetical exercises but strategic moves in a grander philosophical debate about the nature of reality and observation. The EPR paradox, a bold assertion. In 1935, the debate took a significant turn with the publication of the EPR paper, authored by Einstein, Podolsky, and Rosen. This groundbreaking paper sought to demonstrate that the properties of particles could be determined without direct observation, thereby challenging the completeness of the Copenhagen interpretation. According to EPR, if one could know the polarization of one photon, the polarization of its entangled twin could be instantaneously known, regardless of the distance separating them. This phenomenon, known as quantum entanglement, suggests that particles possess an intrinsic reality independent of observation. Bohr's philosophical rebuttal. Bohr's response to the EPR paradox was as ingenious as it was philosophical. He argued that observing one photon could semantically disturb the other, introducing a form of influence that was not physical but conceptual. This notion of semantic disturbance was Bohr's attempt to reconcile the seemingly paradoxical nature of quantum mechanics. However, Bohr did not provide a concrete mechanism for this influence, nor did he address the vast distances over which it could theoretically operate. This response marked a departure from the traditional Copenhagen interpretation, which primarily dealt with physical disturbances and measurements. The EPR paper has since become one of the most cited scientific papers of the 20th century, sparking a multitude of analyses and experimental investigations. Its legacy lies not just in the theoretical challenges it posed, but in the experimental quests it inspired. Gissin's experiment, testing the boundaries. In 1997, Nicholas Gissin and his team at the University of Geneva conducted a landmark experiment that breathed new life into the EPR paradox. They used entangled photons and sent them in opposite directions over significant distances. The results were astonishing. Changes in the state of one photon appeared to influence the state of the other instantaneously, despite being miles apart. This experiment suggested the possibility of semantic influence and raised profound questions about the speed of light as the ultimate limit for information transfer. Observer-created reality, a paradigm of controversy. The notion of observer-created reality stands as one of the most contentious and intriguing ideas in quantum physics. Critics argue that this concept blurs the line between objective reality and subjective observation, suggesting that particles do not possess definite properties until they are measured. This radical departure from classical physics challenges our fundamental understanding of existence. In the realm of classical physics, the act of measurement is straightforward and largely non-intrusive. Instruments can detect and measure phenomena without significantly altering them. For example, one can measure the temperature of a liquid or the speed of a car without fundamentally changing these entities. This allows for a clear, objective description of reality, where phenomena exist independently of observation. Quantum physics, however, operates under a different set of rules. At the quantum level, particles such as electrons and photons exist in a state of superposition, where they can occupy multiple states simultaneously. It is only when these particles are observed that they collapse into a single state. This implies that the act of observation itself brings the particle into a definite existence, an idea that is both fascinating and perplexing. The challenge in quantum physics lies in the fact that observing a quantum particle invariably involves interacting with it using particles of comparable energy. For instance, to detect an electron, one might use photons of light. However, these photons can impart energy to the electron, altering its state. This intrinsic disturbance means that it is impossible to observe a quantum system without affecting it. As a result, the measured properties are, in a sense, created by the very act of observation. Critics argue that the concept of observer-created reality muddies the waters of objective science. If particles do not have definite properties until observed, then reality itself becomes a fluid, dynamic construct dependent on the observer. This undermines the objective, independent nature of reality that classical physics so robustly defends. The philosophical implications. The concept of observer-created reality has significant philosophical ramifications. It poses queries concerning the essence of life and the boundaries of human understanding. According to quantum mechanics, making an observation affects the system being watched actively rather than passively. This implies that, contrary to what classical physics would have us believe, the universe is not entirely deterministic, and that measurement itself is a key factor in establishing a system state. This raises an interesting question. If our observations are always impacting the events we try to investigate, can we ever completely understand the universe? If each measure modifies the condition of the item being measured, then the objective reality that we are trying to understand might be inherently elusive. The very instruments we employ to study it will always have limitations on our comprehension. This also begs the question of whether, in the absence of observation, the cosmos exists in a concrete form, or if it always exists as a potential state ready to be realized by an observer. The idea of superposition in quantum physics, which allows particles to exist in several states concurrently until observed, best illustrates this. This suggests that reality is, in a sense, participatory, challenging the traditional idea of an autonomous reality that exists whether or not we perceive it. Deep philosophical problems concerning the nature of reality and our place in it are raised by these queries. If the universe is shaped by our observations, then our job as observers is not limited to finding an already known truth. Rather, we must take part in the process of creating reality. Even if this concept defies common sense, it compels us to reevaluate our definition of knowledge and our level of cosmic comprehension. It implies a more intricate interaction between the observer and the observed, in which observation is a basic component of the universe's existence in and of itself. The debate continues. This debate delves into profound philosophical issues, weaving through the intricate fabric of reality, knowledge, and existence. It shines a spotlight on the stark disparities between classical and quantum physics, inviting us to reevaluate our perception of the cosmos. At its core, the concept of observer-created reality serves as a nexus point in the realm of quantum mechanics, sparking continued exploration and philosophical contemplation. Classical physics operates within a framework of determinism, where the universe unfolds according to strict laws independent of observation. However, the advent of quantum mechanics shattered this notion, revealing a reality where the act of observation wields profound influence, shaping the very fabric of existence. This paradigm shift challenges us to confront the limitations of our understanding and grapple with the enigmatic nature of reality itself. It beckons us to question whether our observations merely unveil an existing truth or actively participate in the creation of the universe. As scientists and philosophers delve deeper into the mysteries of quantum mechanics, the concept of observer-created reality remains a fertile ground for exploration. It propels ongoing research endeavors and fuels philosophical discourse, pushing the boundaries of our comprehension and inviting us to glimpse the profound intricacies of the cosmos. A conclusion. The progression of physics has continually guided humanity towards ever more intricate understandings of reality. Initially governed by the straightforward Newtonian laws of motion, science soon uncovered the existence of invisible fields that, despite their intangibility, could produce similar types of motion. This discovery paved the way for the profound challenges posed by quantum physics. In this discussion, we explored how classical phenomena related to energy contrast starkly with the principles of quantum physics. The law of the conservation of energy, which underpins the principle of causality, is a cornerstone in both physics and broader philosophical contexts, including Islamic theology. This principle asserts that the universe, as an effect, must have been originated by a capable creator. Consequently, the classical assertion that energy cannot be created is reevaluated within the context of energy being a contingent entity requiring a creator. The second law of thermodynamics, often generalized, is shown to be inapplicable to many natural processes involving growth and revival. This raises questions about the concept of a heat catastrophe and suggests that the universe, exhibiting high order, cannot be a closed system instead. It requires constant maintenance by a transcendental creator. The ability of remote charges to induce fields challenges the principle of spatial locality in cause and effect, highlighting the need for a robust reasoning framework to interpret scientific results. The Copenhagen interpretation, lacking this framework, added confusion to the philosophical aspects of quantum physics. Our sensory limitations isolate us from the quantum world, accessible only through measuring instruments that disturb the events under observation. This disturbance complicates our understanding of quantum reality. Empiricist interpretations of quantum phenomena, such as the claim that electrons have no reality before observation, have led to philosophical debates. A more rational interpretation of quantum events requires integrating inference approaches alongside observation. Faraday's affirmation of the reality of fields based on their effects and Einstein's insistence on the corpuscular reality of electrons, regardless of their behavior, offer a more objective understanding of the quantum world. While quantum events may appear random, they are controlled in ways that give rise to deterministic phenomena in the classical world. Physicists must accept that, despite potential future advances, the quantum enigma may continue to evade full comprehension due to inherent limitations in our knowledge. The quest to understand the quantum realm is ongoing, reflecting the perpetual challenge of pushing the boundaries of human understanding. Thanks for listening, and please don't forget to hit the like and subscribe buttons, and also click the small bell icon to receive a notification every time a new free audiobook has arrived. Thanks again.